This is lecture 19. This is lecture 19, and last class we have discussed the different techniques for sketching root locus. Particularly, we have discussed that 5 different rules for sketching root locus. Today, we'll discuss another 2 rules. So let us start with this example that we have solved in last class. That is how to find that real axis breakaway point or break-in points. So this is that characteristic equation we considered, and this is that G of S and H of S. Then for finding that real axis breakaway point, we need to find that dk by ds, and if we just equate to 0, then we get two values, that is s1 equal to this one and s2 equal to that one. So let us draw the root locus based on the rules that we have discussed. So this is that S-plane, this is sigma, this is j omega, and if you look at that g of s, h of s, then two roots are there. One is at -1, another one is at -2. So we have two poles at -1 and at -2, and that open loop 0, they are at +3 and at +5. So one is +3, another one is +5. So now we have already discussed that whenever k equal to 0, that root locus starts at open loop poles and ends up at open loop 0. So the root locus, and if you just look at that which segment of the real axis, the part of that root locus, so this is that segment, because if you just see on the right hand side, that number of poles and or zeros could be that even number. So here on the right, if you see, this is 1, and this part, that means if you look to that right, that would be 3, because 1, 2 and 3. So these two parts belong to that root locus. Then we have seen that there is a point which is -1.45. So -1.45 is inside this particular segment, and other one is that S2. So this is inside this particular segment. So this particular point is called that breakaway point, and this point is known as break-in point, because if you start increasing that value of k, then at that particular point, two roots become imaginary and they start going away from this real axis, and so this is that arrow, and if you keep on increasing that value of k, then at that particular point, so this is that point and this is another point where they cross that imaginary axis, And if you keep on increasing that value of k, so then again at breaking point, two roots, again it would be real, and then finally when k tends to infinity, they reach at open loop 0. So this is actually that root locus for this given open loop system. So here one point we have noticed that when we increase that value of k, so at some particular value of k, two poles cross that imaginary axis. So now we are interested to find that value of k and at which point they will be crossing that imaginary axis. So this is that rule 6, that j omega axis crossing. The j omega axis crossing. So for finding j omega axis crossing, we need to apply that Routh-Hurwitz criterion, and from that Routh table we'll be able to find what would be the value of k and at which point they cross that imaginary axis. So this is the Routh-Hurwitz criterion is used to find the j omega axis crossing and the corresponding gain k. So as we know, whenever we form that Routh table, then two poles will be on the imaginary axis. That means there will be a value of k at which two poles would be complex conjugate poles and they lie on the imaginary axis only when a row in a Routh table would be 0. That means we would have one auxiliary equation. So let us see for this particular example. So here this is that open loop transfer function, and this is the characteristic equation. If we just write the characteristic equation, the polynomial that you would have, that is a square plus 3s plus 2. So we have multiplied this, so this one, and plus k into that plus k into a square minus 8s plus 50 equal to 0. So this is that polynomial for this particular problem, and if we write it, so taking a square common, then s plus s into 3 minus 8k plus 2 plus 15 k equal to 0. So this is the characteristic equation, and then we are interested in to form that Routh table. So that is s square, s1 and s0. So s square, that would be k plus 1, and here it is 2 plus 15k, then 3 minus 8k, and it would be 2 plus 15k. So this particular row, it would be equal to 0. So then what would be that value of k? That is 3 minus 8k, that would be equal to 0. So k equal to 3 by 8. So that means that the value of 3 by 8, both the roots would be on the imaginary axis. And what would be that auxiliary equation? That means if you go one step above, so that is, if you replace this value of k here, so that would be 11 by 8. So that auxiliary equation it becomes, so that as, if you just replace that value of k, so it would be 11 by 8 a square plus 61 plus 8. And from this particular auxiliary equation, you can find what would be the roots. That means whenever it crosses that imaginary axis, we get this value k. So this k is 3 by 8. This is 3 by 8. So that means the value of this k is 3 by 8. And we can find this particular root just by solving this auxiliary equation. So here, this is that rule 6. So whenever that root locus crosses that imaginary axis, just by applying Routh-Harris criteria, we can find at what value it will cross that imaginary axis. So the last rule is called that angle of departure and arrival. So that is angle of departure and arrival. What is this? So this particular concept is required whenever we have complex conjugate poles and zeros. So that thing you can understand from here. That is, so so we need to just please wait for 1 minute. I need to just open this file. So we are discussing here that angle of departure and arrival, and this particular concept is required whenever you have that imagine that complex conjugate poles and zeros. What is that? So suppose you have one pole here and one pole here. They are complex conjugate. So we know that when k equal to 0, then that root locus starts from that pole, open loop pole. So now the question is, when k starts increasing, then how that closed loop pole will be changing and what would be its direction? Means whenever at k equal to 0 you are here, when k starts increasing, it may move along that direction or along that direction. So any directions it can move. So here we need to know along which direction these closed loop poles will be moving. So that particular concept is called that angle of departure. That means along which direction. So that is that angle we need to find along that direction. Whenever we increase that value of k, the closed loop pole will be moving from the complex conjugate pole. That is called that angle of departure. And the same thing happens whenever we have, suppose, 0, two complex conjugate zeros are there. So whenever k tends to infinity, so then we know that root locus reaches at open loop 0. And when they are complex conjugate 0, so then the same thing happens, just reverse to that open loop complex conjugate poles, that along which direction it will reach to this particular 0. So that angle is called that angle of arrival. So now we are going to discuss that how to calculate that angle of departure and angle of arrival. So that is the when complex conjugate pole and or 0 exist, we need to find angle of departure or arrival. So let us understand this particular method by some example. So suppose we have one loop transfer function, that is k g of s h of s, that is equal to k s plus 2, then that is s plus 3 s square plus 3s plus 2. So if this is that open loop transfer function, from here it is clear that you have that complex conjugate poles. So let us first draw that root locus. So here you have that real axis and imaginary axis. So this is that S plane. Now we have a pole at -3. So a pole at -3 and two zeros are there, two poles are there. So if you calculate those poles, so that would be here, that is S1 and 2. So it becomes 1 plus minus j. So that means here you have that -1 minus 1 plus j, and here you have minus 1 minus j, and there is one 0 that is at minus 2, here minus 2. So now, as it has that open loop complex conjugate poles, that means we need to find out that what would be the angle of departure, because so at that particular point that root locus starts and it is at k equal to 0, the open loop pole would be the closed loop poles. That means they would be here at the pole location. And if we just see, that means whenever your open loop transfer function is like that, so it has 3 open loop poles, finite poles, and one finite 0 at minus 2, and you can see here that it has 2 zeros at infinity. And from rule 4 we have seen that whenever it has zeros at infinity, we need to find that centroid and asymptotes. So let us first find what would be its centroid. So the definition, that formula for finding centroid is like that: the summation of finite poles minus summation of finite zeros divided by number of finite poles minus number of finite zeros, and that angle of asymptotes equal to 2k plus 1 pi divided by number of finite poles minus number of finite zeros. So if we apply those formulas, so then we will get that centroid that sigma, so summation of that open loop poles, so that is minus 3, and here that you would have plus j and minus 1 minus j, and that finite 0 is at minus 2. So here you can see that you have 3 finite poles and 1 0, so that is 3 minus 1. So one interesting thing you can see here, that means as the poles are complex conjugate poles, so this one would be cancelled out, and this value is minus 3 minus 4 minus 5 plus 2, so that is 3 by 2 minus 3 by 2, so that equal to minus 1.5. So that is that centroid. And angle of asymptotes, so angle of asymptotes, that theta equal to 180 degree divided by 2, that is 90 degree, and when it is k equal to 0 and k equal to 1, that would be 270 degree or minus 90 degree. So that means here you can see that centroid is at minus 1.5. So this is that point which is minus 1.5, and angles are 90 and 270. So basically your asymptotes would be like this. So now we are interested to find what would be the angle of departure. So if we consider a point very close to this particular pole, and that particular point would be on the root locus means it must satisfy, so a point on root locus, so that means the must satisfies that angle criteria. That thing we have seen, that k of g of s h of s equal to 2k plus 180 degree. So now here we can see that if we draw the vector from this pole, open loop pole, and this 0, and here you have one pole. So this is that reference axis, that is that 0 degree. So now you can see that we have considered a point which is very close to this particular pole. So then that point would be on the root locus if it must satisfy it satisfies that angle criteria. So the angle criteria means we need to find what would be the angle contribution for this particular pole. Suppose this is theta 1, this is theta 2, and this one is 90 degree because they are complex conjugate. So from this particular pole, if you draw a line, so it would be perpendicular with respect to that reference point. So what would be the angle contribution for this particular pole? That is theta 1, and you can see here that pole is at denominator, so its angle contribution would be negative. That means that is minus theta 1. And what would be the theta 2? Theta 2 is the angle contribution due to this 0, and as it is in the numerator, so its angle contribution would be theta 2. And here there is a pole, so its contribution would be 90 degree, and as it is pole, so it would be minus 90 degree. And there is a point which is very close to this particular pole. So if we draw a vector from that pole, that point to this pole, so that angle actually we do not know, and here our objective is to find that angle. So that angle would be the angle of departure. So that angle is suppose theta, and as it is associated with the pole, so its contribution would be minus theta. So whenever that point is on root locus, that means it must satisfy this particular angle criteria, so that would be equal to 180 degree. So now from here we can find what would be the value of theta. So let us see what is theta 1. So here we can find what is theta 1. So this particular length is 1, and here we can see that this length is also minus 1. So that means from here to here, this length is coming 2. So that means this theta 1. So theta 1, we are getting that theta 1, that is tan inverse 1 by 2. And what would be theta 2? So theta 2 is this angle. So theta 2 is tan inverse. So this length is 1. This is 1. So that is tan inverse 1 by 145 degree. So let us write this particular equation. So theta 1 here minus theta equal to 180 degree plus 90 degree plus 90 degree. So plus theta 1 minus theta 2. So here theta 1, so that is 270 degree plus theta 1. So theta 1 is this one, so that is 26.56 degree, and that theta 2 is minus 45 degree. So you would have that angle 251.6 degree. So theta equal to minus 251.6 degree, or it would be 108.4 degree. So that means this angle is called that angle of departure. So that is 108.0 degree. So here you can see what happens. So if we take that, this is that reference, and here this is that angle 108.4 degree. So that root, so basically that whenever k varies, then that root locus will go like this. And you can see here when k tends to infinity, that root locus follows that asymptotes and it would be straight line. And in this particular one, so the root locus is going from -3 to -2, and here two branches are like that, and this angle is called that angle of departure. So if we take one more example, so suppose we have a closed loop system, and that open loop transfer function is given like this, that is k of s square minus 4s plus 20, and this is s plus 2, s plus 4. So here this is that reference comment, and you are asked to draw that root locus for this system, and here that open loop system is given, and this is that parameter gain is varying. So in this case, if you look at the numerator part, here you can see it has two complex conjugate zeros, and those zeros are S1 and S2. If you find those zeros, so it would be plus 2 plus minus 4j. So these all are these two complex conjugate zeros. And in rule 7 we have discussed that we need to find that angle of arrival whenever you have that complex conjugate zeros. So let us first draw that root locus here, that is, so this is that sigma and this is j omega. So you have two poles, one is at -2 and another one is at -4. Two poles are there and two complex conjugate zeros. So here you have a 0 and its value is 2 plus 4j, and here 2 minus 4j. So now which part of the will be the part of root locus? So this part, and you can see that whenever k equal to 0, the closed loop poles would be that open loop poles. So that means your root locus will start from -2 and -4, and when we keep on increasing that value of k at a particular value inside this -2 and 4, that is that breakaway point, it will go like this, and there would be a point where the roots cross that imaginary axis. And now here the question is, whenever k tends to infinity, when k tends to infinity, how that root will reach to this particular 0. So that means we need to find what would be the angle of arrival. So we will be following the same technique. That means if you consider a point which is very close to this 0, and if we draw that vector, so this is that reference angle, so this is that reference angle, so that is 90 degree. And here if we take that, say suppose this is theta 1, this is theta 2, so then what would be that angle condition? So the angle condition is theta 1 due to that pole, so that means minus theta 1, and that would be minus theta 2 because this is a pole. And here you can see this is that 90 degree because it is 0, and if you take a point which is very close to that 0, so its contribution we do not know, that is that angle of arrival. So suppose that is theta, so this one would be equal to 180 degree. So now we can see what is that theta 1. So this length is 2, this length is 2, and this is 6. So total this base is 6. So that is minus theta 1 equal to tan inverse. So this length is 4. So that is theta 1 equal to that 4 by 6. And what is theta 2? Theta 2 here, this is 2, that is 4 and 4. So that is theta 2 equal to 45 degree, 90 degree plus theta equal to 180 degree. So here this one is 33.69 degree minus 45 degree plus 90 degree plus theta equal to 180 degree. So from here you will calculate that theta and you will get that theta equal to 168.69 degree. So this is that angle of arrival. That means if you take that this is that reference vector and say suppose this is that angle, what is 168.69 degree. So at that particular 0, so it will come like this, and it is symmetric, so it also reaches to that 0 following this particular angle. So this angle is called that angle of arrival. And here for finding this particular breakaway point, what we need to do, that means we need to write that k in terms of like so k from characteristic equation we can write that k equal to minus of 1 by g of s h of s. So it will go to that numerator, so that means it would be minus s square plus 6s plus 8 divided by s square minus 4s plus 20. So you can see it here, s square plus 6s plus 8, and you'll get this one. So we are getting it from the characteristic equation. And now if you find that dk by ds, so you will get that expression, and if you equate it, so basically that value of s when dk by ds equal to 0, it gives you that breakaway point. And if you solve that on, you will get that 5 square minus 12s minus 76 equal to 0, and here you will get two values. So one value is 2.86 and other value that you will get, say, 5.28. So I would suggest you to calculate on your own, and then you will see that we'll be considering only that value because that value is not the part of root locus, as you can see. So the part of that real axis, that means from -2 to -4, it is only the part of root locus, and this is that point minus 2.86. So this is that point inside that -2 and -4, which would be the breakaway point. The other points 5.28, it is outside that segment. It is outside that segment. So that means it is not the point that lies on the root locus. So in this particular example, what we have seen, this is that closed loop system, and if we just consider that transfer function, we can see that it has that complex conjugate 0. So we can find that angle of arrival, and we have calculated it, and this is that breakaway point. And then we can see that means at what value of k it crosses that imaginary axis. So from rule 6, we can see that for finding that one, we need to do that Routh-Harris criteria. We need to apply that, and from Routh table we can find it. So let us see. That is, your characteristic equation is 1 plus k s square minus 4s plus 20, and that is s square plus 6s plus 8 equal to 0. So if you write that characteristic equation, you would have s square plus 6s plus 8 plus ks square minus 4ks plus 20k equal to 0. So now if you take that s square and this term, so that is s square plus k plus 1, then 6 minus 4k s plus 8 plus 20k equal to 0. So now we need to form that Routh table. So that is s square and s0. So now you have k plus 1, 8 plus 20k, and here you have 6 minus 4k, and here you have 8 plus 20k. So two poles will be on the imaginary axis. That means one row would be equal to 0. So this one would be equal to 0. And as we are dealing with that was negative feedback structure, so that means k greater than 0, k is varying from 0 to infinity. So this term is positive, this term is positive. So at what value of k this particular row would be equal to 0? So that is, you can see that 6 minus 4k equal to 0. So k would be equal to 6 by 4, that is 1.5. So what is your auxiliary equation? So that auxiliary equation, that means you need to go one step above, and if we just replace that k equal to 1.5, we will get that auxiliary equation, that is as equal to 2.5 s square. So we have replaced the value of 1.5, that is 2.5 s square, and here if you replace that k, you will be having 38 equal to 0. So now you can take the dA by ds equal to 5s. So that means here you can just replace with that 5, and from this particular auxiliary equation, you will be having that two roots that would be lying on the imaginary axis, that is plus minus 3.898j. So this is that value, this is that point 3.898j, and this is that value of k. So that means if you go back to that root locus, so this value what we get, that is 1.5, and these particular points are actually 3.898 j. So this point is 3.898 j, and this is minus 3.898 j, this particular point. So this is your complete root locus. So in this particular example, what we have seen, as that system has imaginary complex conjugate zeros, so then we can find that angle of arrival, and here we have calculated, that means at what point and what value of k it crosses that imaginary axis. We just got it applying that Routh-Harris criteria, and here we have also calculated what would be that breakaway point just by taking derivative of that. So these are the 7 rules that we have discussed. So let us summarize what are the rules for sketching that root locus. First of all, the number of branches. So number of branches is equal to the number of closed loop poles. And the second one is how that root locus varies. That means whenever k equal to 0, that open loop poles and the closed loop poles are in, and when k tends to infinity, we have seen that the root locus ends up at open loop 0. Then as the second rule is that symmetry, as the characteristic polynomial is a real coefficient polynomial, so it is symmetric with respect to that real axis. Third one is that real axis segment, and here we have understood part of that real axis belong to the root locus. So we need to just calculate that odd even number, and from there we can find which part of that real axis belong to the root locus. The fourth rule is that centroid and asymptotes. So this particular concept comes into picture whenever that system has zeros, open loop system has zeros at infinity, and we have seen the two formula here, the angle of asymptotes and for finding centroid. And that fifth one is that real axis breakaway and break in point. So that means there would be a value of k whenever the closed loop poles will be just going away from that real axis. That means roots would be complex conjugate, and then if we keep on increasing that value of k at a particular value of k, again they will come to the real axis, like here real axis. That means again two roots would be real, so that is called that break in point, and this is called that break away point, and we can find it just by taking derivative of that k with respect to s and equate it to 0. And then the sixth one is that j omega axis crossing. We can find it applying that Routh-Harris criteria. The seventh one is that angle of departure and angle of arrival. So that particular concept comes into picture whenever we have that imaginary poles and zeros, that means complex conjugate poles and zeros. So let us discuss one more that concept what is used in root locus, that is called that root sensitivity. So this concept is also very important, that is that root sensitivity. So this is also known as that pole sensitivity. So this is actually the ratio of the fractional change in a closed loop pole to the fractional change in the system parameter. So what we have seen, that means whenever we consider a closed loop system, And in root locus, we consider a parameter that is k, gain, and when that gain changes, that closed loop poles also will change. So this root sensitivity says that if there is a change in gain, what would be the change in closed loop poles? So that ratio is called that root sensitivity. So the definition is, this is that ratio. This is that ratio of the fractional change in a closed loop poles to the fractional change in a system parameter. So here that system parameter is that k, and so we can just say that this is that sensitivity. So sensitivity is equal to delta S by S. So that means that is the change in that pole divided by delta K by K. So here, from here we can see that this is that expression for that root sensitivity. So here you can see that this is that fractional change in pole whenever there is a fractional change in that parameters, in the gain. So that ratio is called that root sensitivity. And interestingly, this root sensitivity is a vector quantity. That thing we can understand from an example. So I think whenever we have started discussing that root locus, the first lecture on root locus, we have discussed one example, numerical example. You can see that example, and I am just taking some data from that example. So this is that example. So we have given all the data in that particular lecture, the first lecture on root locus. Let the characteristic equation be a square 10s plus k. Suppose we have a characteristic equation like that. We are trying to find what would be that root sensitivity. So here you can understand that whenever this k varies, then those functions, those s, that means that roots, are the function of k. So then we can take the derivative of that s with respect to k. So then we can find that ds by dk plus 10 ds by dk plus 1. So here k is the variable, and from here we can find what is that ds by dk. So that would be equal to minus 1 by 2s plus 10. So what is your sensitivity, root sensitivity? So root sensitivity s equal to, we have seen that formula, that is k by s into del s by del k. So here you can see that k by s into del s by del k is this one. So that is, if you just put it here, that is minus 1 by 2s plus 10. So you would have k by s into 2s plus 10. So that is that root sensitivity, and this is actually a complex quantity. This is a complex quantity, So let us take those data. So we found that, so here I am just writing, see the example we discussed in the first lecture on root locus. So from that example we are taking data, that means we get that S equal to, so the location of that pole was minus 9.47 when K was 5. So in that case, what would be the root locus? What would be the root sensitivity? So root sensitivity, that is S, equal to, here you can see that that is K by S into del S by del K. So S by, that is K minus, that is 5, that is K, and here that S is minus 4.7. So this is that S and this is that K. We are just replacing here K by S and del S by del K. So del S by del K we have already calculated. So then if you just replace it here, that is minus 1 by, so that minus already we have taken here, this minus already we have taken, this minus, so that is 2S. So here the S is minus 9.47 into 2 plus 10. So if you calculate it, you will get that value equal to 0.059. So this is that root sensitivity. And if you look at that root sensitivity, that expression, this one, so then what will you get? What would be, so you can write it here, K into S, that is delta S, the change in that root, and this is the delta K, change in that K. So here, from here you can, so this is equal to S, the root sensitivity. So then you can find what would be the change in that root, that is delta S equal to, this is small s by K, and that root sensitivity, this one, into delta K. So here this is that root sensitivity. So now we are interested to find what would be the change in the delta S. So that would be that root sensitivity into small s by K into delta K. So here we get that root sensitivity 0.59 into that pole is at minus 9.47, K is 5, and delta K, suppose you take the 10% change in, suppose we consider 10% change in K. So 10% change in K means your K was 5. So if you take 10% change, so that means that would be 0.5. So here you will get, if you just multiply those terms, you will get that 0.056. And here this is a scalar quantity, so basically 0 degree. So that means what happens whenever your K is 5, and if you just consider 10% variation in 5, then the closed loop pole will be shifted along the x-axis, so moves towards right 0 degree. So here we can say that this move towards right, because that this is scalar, so we can consider that this scalar into that 0 degree angle. So whenever you take 10% change in K, the closed loop pole will be changing towards right with this particular value 0.056. So from root sensitivity you can calculate in the root locus how much change would be there. Similarly, if you take some other value of k and you can get that s equal to complex, so then just by applying this particular formula you can easily find what would be the change in k. So this is called that root sensitivity. So the last topic in root locus, that is that root locus for positive feedback system. So far we have discussed root locus for positive feedback system. So far we have discussed that negative feedback structure. So now I'll be just giving you the idea. That means whenever we consider positive feedback structure, what would be the difference with the negative feedback structure that we have discussed so far. So let us first consider that closed loop control system, that is k of g of s, and here you have that h of s and this is ys. So here this is that command input, and here you can see this is that positive feedback, and here you have that parameter, this k is varying and with positive feedback. So in this particular case, the rules that you have discussed, that means that 7 rules, how those rules will be changing if we just consider positive feedback. So here the transfer function, let us write that transfer function, that closed loop transfer function would be equal to that k of g of s 1 minus. In case of negative feedback it was plus, so here it would be 1 minus k of s, k into g of s h of s. So from here it is clear that, so this is that characteristic equation in case of positive feedback, and poles of the closed loop systems must satisfy again that angle condition and that gain condition. So here poles of closed loop system satisfy. So if we just write this characteristic equation, so what we will get, so that is k of g of s h of s would be equal to 0. So this is the characteristic equation. From here we would get that k g of s h of s equal to 1. So now this 1 is nothing but that is 2k, or we can write that 2k pi, that is that angle. So that means if we write that this is that angle, and here that k equal to 0 plus minus 1 plus minus 2, so that means the angle would be, so that is that angle, we can say that 360 degree. So this particular condition should be satisfied just like that negative feedback structure. So only here the difference is that sign. So whenever it is plus, so that is one angle k 360 degree. So this is that angle criteria, and from here you can see you have two things. One is that gain, that is k should satisfy that g of s h of s. So this is that gain criteria. And what would be the phase criteria? That means the angle k of s g of s h of s, it must satisfy that angle k 360 degree, where k equal to 0 plus minus 1 and so on. So you can see the difference with the negative feedback. So in case of negative feedback, we also had the same gain condition, but the phase condition, it was 2k plus 1, 180 degree. And here the phase condition is 360 degree. So that means if you just see the axis, so basically here that would be along that point, so that means this is 0 degree, and in case of negative feedback it was along this axis, so that means it would be either 180 degree or minus 180 degree and like that. So that is for that negative feedback case, and for positive feedback case it is along that particular axis, that is 0 degree or 360 degree. So this is the difference. So now if we just consider this particular fact, the difference in that rule. So first of all, no number of branches. So number of branches, basically no change, because the number of branches would be equal to the number of closed loop poles. So it is similar to that negative feedback case. Now what about the symmetry? Symmetry, again there is no change. So that means in case of positive feedback, that root locus also symmetric with respect to that real axis. So then let us see that real axis segment. So here there would be a change, that real axis segment, because you can understand that whenever you have, suppose a poles and poles here, another poles here. So in case of, and suppose you have a 0 here, in case of negative feedback, what we have seen, that means this particular part is actually this segment, and that segment would be the part of that root locus. The reason is we consider that angle 180 degree, but here you can see, that means if you consider this particular point, then this is minus 180, and the contribution of this one is 0 and this one is 0, so it does not satisfy this particular condition. But if you consider the point here, so then you can see the contribution for this one is 180, for this one is 180, that means that would be 360 and from 0. So that means this point, this particular point is satisfying this particular point is satisfying this angle condition. So that means this segment is the part of root locus. So that means the segment in the real axis, which are the segments in the real axis which are the part of the root locus in case of negative feedback, complement to those segments would be the part of the root locus if you consider that positive feedback. So let us write that is on the real axis. So on the real axis, so that means it is very clear that if you just consider this angle criterion, and if you apply the same concept that we have discussed in case of negative feedback, it is easy for you to find which segments would be the part of root locus. The root locus exists to the left of n. So here you can see that is even. In case of negative feedback it was odd. In case of positive feedback it is even number of real axis finite open loop poles and or finite open loop close. So this is that difference, and that difference due to the angle condition. And if you just see the difference with that negative feedback, here you can see that real axis segment, it was odd. So basically in case of negative feedback it was odd, but in case of positive feedback it is, the count would be that even number. You can see here it is even. So this is that difference, and that difference appears because of this angle condition. So we have seen here, that means in the rule 3 there is a difference whenever we consider that positive feedback. And what would be the starting and ending? Starting and ending. So there will be no change. That means that root locus start at the open loop poles and it ends up at open loop zeros. So there is no change, and there would be a change in the calculation of centroid and the angle of asymptotes. So basically for finding centroid there is no change. So centroid and angle of asymptotes. So for finding centroid, no change. The formula remains same. But what would be that theta? As you can see, in case of negative feedback, that centroid, whenever we calculated centroid, that angle of asymptotes, it was 2k plus 1 pi. And obviously here that angle would not be 2k plus 1 pi. So it would be 360 into k. So the angle would be 2 pi k. So in place of 2k plus 1, it would be 2k, because in case of positive feedback that angle condition is changed, and here number of finite poles minus number of finite zeros. So here there is a change in that formula, and here this k is that 0 plus minus 1. So what we have seen, that means in place of negative feedback, if we consider positive feedback, what are the changes that we can see in the rules for sketching that root locus? That changes occur because of that angle condition, because in this case the characteristic equation would be 1 minus k g of s h of s equal to 0. So the angle condition is this one, and because of that angle condition there is a change in real axis segment, and there is a change in the formula for finding that asymptotes. And in other cases you can see that angle of departure or angle of arrival, so there we have equated to 180 degree. So in this case it would be 0 degree, or you can write 360 degree. So these are the changes. What is its application? So you can see that the application of this particular concept, say suppose we have one closed loop system, and this is that gain k. So suppose this is that gain k here, and this is the reference command. It's a negative feedback. So far in the negative feedback structure we have considered k greater or equal to 0. So k greater than 0. So now if we consider what would be the root locus if we consider k less than 0. So that means what would be the root locus whenever k is negative. So when k is negative, so we can just put one negative sign here, and we can say that okay, k would be positive. So if we just put negative here, and if we bring this negative sign here, so it would be plus positive. And then what happens if we consider the case what is the root locus when k is negative, varying from minus infinity to 0. So in that case we can say that minus of k, or we can say that k is varying in positive range, that is k less than infinity greater equal to 0, k is varying in that range with a negative sign, and if we bring that negative sign here, so that would be basically positive feedback. So this is, and once it is positive feedback, we know that what would be the root locus with positive feedback. That means we can apply those rules that we have discussed, and we can draw the root locus. So this is that concept we can apply. So what we have discussed in the root locus. So here there are the 7 rules for sketching that root locus, and we have solved some examples to understand those rules. And then we have defined that what is that root sensitivity. So root sensitivity is a complex quantity, and it gives it that value as well as the directions. That means along which direction it will move, that closed loop poles will move once there is a change in that parameter. And this is that root locus for positive feedback system. So there would be a change related to that angle condition, only that angle condition, and associated with that angle condition, as this particular rule is there, that is that rule 3, real axis segment, and that finding that centroid as well as angle of arrival and angle of departure. So only you need to change that angle condition, and you can easily draw that root locus. And this is that concept how to apply this particular result, that means root locus with positive feedback. So if we consider that k is varying in the negative range, the minus infinity to 0, so we can represent that particular framework is as a positive feedback structure, and then we can apply those rules for sketching that root locus. Thank you.